All right, everybody. Here we are to talk about Rene Descartes. Yay. And as we look at Rene Descartes, we see we're getting really close to the calculus controversy, which is the second controversy for our course. That's actually going to be the next lesson's worth of material. And as we get there, we're rounding out the end of our material for our course. I would like to talk a tiny bit about Newton and Leibniz, and then a little bit about Gauss. There's a lot of other more modern mathematicians out there, but unfortunately we just don't have time to get through all the way up to 20,000s, or 2000s, the 2000s. So we'll get as far as we can, and then we'll start talking about wrapping up our course. So Rene Descartes, he's French. He's actually from Le Hay. His dates are 1596 to 1650. So you can tell by this death date, 1650, we're just, like I said, barely 2020s, right? Okay, so barely in the 2000s here. So this is less than 400 years ago, so this is getting really, really close. Mentioned in one of our more recent videos about Columbus sailing the ocean blue in 1492. However, we're not quite to the birth of our nation yet, the actual signing of our Declaration of Independence, right? 1777 kind of thing. So we're getting there, but we're not quite where we should be yet. Okay, so we're still mostly focused in Europe. Our course will not include any real mathematics from America, but you can see why, right? We're still, in America, we're still trying to figure out how to harvest crops and probably do hunting and gathering and stuff like that. So in America, we're a little more primitive than what these guys are. All right, so what we see about Rene Descartes is that he actually seems to be a follower of Copernicus, but an interesting little fact of him is that he actually withdrew one of his works from publication whenever Galileo had his trial. So after Galileo was found to be, I forget exactly how it was worded, like an extreme heresy, right? After that happened, vehement suspicion of heresy, that's what it was. So after that trial took place and he was named a heretic and sentenced, Rene Descartes pulled one of his books, okay, or one of his papers that was up for publication. We know a little bit about his early life. He left school at 16 because he wanted to travel. He just seemed unhappy with his education. Apparently they weren't challenging him enough. They weren't giving him enough of what he wanted. So he thought that he could learn more at traveling, going places. So for 12 years, he went to all over the place. He went to Paris and Holland and different places like that. Now these places, especially Holland, were considered a little more liberal, a little probably more likely to accept more liberal thought processes like Copernicus's ideas. And so he settled in Holland eventually. And while he was in Holland, we can see that he actually made links between geometry and algebra. So we've kind of been dancing around this just a little bit in some of our earlier lectures. We've talked a bit about different people like Al-Khwarizmi who saw some links between geometry and algebra, but it just hasn't ever been, I guess, really formalized until what we see is the Cartesian coordinate system. So we know this one today, right? It seems very obvious to us. You go X and Y, X is left and right, and Y is up and down. But the interesting part about this is if you look at Descartes, look at his name, Cartes, and look at the Cartesian coordinate system, you can see a pretty clear link to his name and how it came to be named the Cartesian coordinate system. So while we take the XY axis pretty for granted nowadays, it's just part of what we do in algebra and geometry, think about it for just a minute. What we have is maybe we have something like y equals 3x plus 2, which is clearly a very algebraic equation, right? And what we have over here is something that's going to give me more of a picture, more geometry, right? So he actually came up and said, look, up and down on the y-axis, this will be my y-intercept, this is a 2, and then, of course, we know, let me label a little bit, sorry. We know that to go from there, we would go rise over run, up 3 over 1, and down 3, 1 to the left, and we see, oops, not quite a straight line, but you get the point. And so what we have here is reflections, those kinds of things. Maybe we can apply those to these very algebraic equations and families of equations and things like that, and maybe we can see what that looks like on this graph. Maybe if I subtract 2, this whole thing comes down, and we see what happens to it pictorially. So it puts a very visual look with a very mathy kind of algebraic equation up there. All right, so some things that he did. He wrote something called The World. Oops, I can't spell today. The World. And basically what The World was is it was talking about Copernicus and Galileo. Oops. Okay, discussing the, let's say, new science and that kind of thing. But what he said was he wrote it not to come against the church. It's not his goal to come against the church. He's writing it to talk about the science, basically. And it's kind of an overall opinion of these new age scientists, what they're doing and the look that they're doing, the math and the data, and then following that up with mathematical models and talking about science that goes with it. It's not to come against the church. We're just talking very academically. We're speaking academically, and we don't want people to be offended by it. The problem with this is because he was a little bit worried about coming against the church was that it was not published during his lifetime. So what that means is that it just kind of sat on a shelf and waited for him to pass away in 1650 before it can come to light and before people can, appreciate, I guess is the word, appreciate the works that he put forward. So another one that he did was a discourse on the method. And by the method, we think that he's talking about Archimedes' method, right? So some conversations about old school math. What he did was he used math-like, I'm going to put that in quotes, math-like proofs to come up with analytic geometry, which there's an entire field of analytic geometry now, and you can take courses of it in college and different things. And seriously, what that does is it's analyzing geometry through the use of algebra. So taking this stuff and applying it. And I'll show you an example of one of the things that maybe we kind of take for granted, which is a parabola and how that looks. And the things we do with it today are not necessarily the things that Descartes would have done in analytic geometry, because he would have used more analytical phraseology and terminology and stuff like that. So you'll see what that looks like. Okay, so we owe him for coming up with putting together for us points and graphing lines and looking at intersections. Intersections of graphs in general. They don't have to be lines. So that's an interesting thought there. He starts looking at those as solutions. So, for instance, if you had a system of equations that were linear, you might say, hey, here's line 1, here's line 2. They cross right there. That is the solution to the system. Right, these two lines. However, you might also have something maybe a little more interesting, where you have a lovely parabola, and then you have a line cutting through. Let's call this one L3. Okay, and when we see that, we see, hey, look, these graphs intersect in two different points, right here and right here, and where they intersect here, those are solutions to this system. So where this system of equations here is this, whatever the equation for this parabola is, and whatever L3's equation are. So he comes up with, hey, look, we can use analytic geometry, use a little bit more formal thinking to come up with solutions of things like that. And we can blame him for all of that. All right. He's also known for, in his works, he has done lots with circles. I mentioned parabolas. There's a ton, I believe, in your book that talks about ellipses and how to come up with very mathy ways to come up with equations for ellipses. Vertices, directrix, that kind of thing. He's very definitely going to have an X and a Y for his unknowns, and for this to be a set of coordinates, right? So these are his points. He's got all of that going for him. He does some work with square roots. And lo and behold, he actually has the notation for x squared, x cubed, and so on. All of those lovely exponents on variables. So by this time, we're actually seeing what is more modern algebra and what we're used to seeing with those variables thrown in there for us. So, yeah. We have Rene Descartes to blame for a lot of this. And he has one very famous saying. I would go so far as to put a little star on this one. And you may have even heard this one before. Usually, whenever I have a face-to-face class, I might even ask, does anybody know his saying? And every once in a while, I'll get somebody who actually knows. Rene Descartes is known for, I think, and therefore I am. That was his quote. This is, of course, more philosophical. It has less to do maybe with math and more to do with his philosophy on life in general. But I think, and therefore I am. That's his famous quote. So on an exam, say the final exam for this course or something, you might be interested in seeing some of that. Okay, so yeah, that's kind of the idea behind him. I want to talk just a minute or two about his analytic geometry and things that came out of it. Stuff that I've already mentioned. So 2x plus 3y equals 6. We can graph this now. Yay. And whenever we say we can graph this now, not only can we graph it, but basically anybody in the world who has studied algebra now graphs that in the same way, on the same coordinate system, with similar motions, right? You're probably either going to find x-intercepts and y-intercepts and plug those in, or else you might solve for y and then you'll have it in slope-intercept form. But working with this and graphing it pretty much come down to the same set of steps in general. I mentioned a second ago, he also worked with circles. So an interesting thing here is that we start getting some definitions coming in. We already have some definitions from the Greeks, so some of that we can steal from them. So for instance, if we're talking about a circle, we need a center, right? A point that is the center of the circle, and we need a radius. So given a point at the center of a circle, the actual circle is comprised of all points a given distance from that center. And we all know that that distance that we're talking about is a radius, right? So in order to discuss a circle, we need a center and we need a radius. So I'm kind of cheating. I put my center here at 0. Let's make our radius be 3. 1, 2, 3. And I will cheat again and just come out on each of the axes, and I'll say, well, I know that these points are 3 units from the 0, from the center, so they must be on my circle, and then I'll just kind of connect the dots. If you're teaching kids or looking more into this, I know this is a terrible graph, I'm sorry. Terrible drawing of a circle. But an idea, if you don't have a compass readily available, is that you could put your pencil in the middle, or you could have a string or something and tack it down in the middle, and then have a certain length, say on the string, and just follow let that string be your radius, basically, and then follow it around. And that gives you know that every point that your pencil or your pen touches has to be the same distance from the 0 once you've tacked down the end of it, or from the center, because that string is the same distance no matter what, right? So that's kind of an idea for an easy fix for a compass if you don't have one. All right, so that's the idea going on behind circles. For us, we see for the first time, x squared plus y squared equals r squared. That's the equation of a circle if you don't know it. And this one is centered at 0, 0, much like the one that I just drew up there, okay? So if it's not centered at 0, 0, then we have to do a little bit of a conversion, which I'll stick in here in a minute. But before I do that, what I'd like for everybody to think about is, remember that R stands for the radius. And remember that a radius is a distance. So if you think for just a minute, if I were to solve for R, I would square root this side. That would get rid of the square, right? And then I would square root this side, and that would be a distance is equal to a square root of this guy squared plus this guy squared. It's basically the distance formula, right? Okay, so I think it's important that everybody kind of knows, hey, this comes from the distance formula, yay. Also, if I look at it really carefully, this looks a little bit like something we've been working with throughout the course on and off. A squared plus b squared equals c squared. So we kind of see a Pythagorean thing coming in here with this circle. And in fact, if you teach trigonometry or pre-cal, you may have even done stuff where you have, for instance, if I'm trying to talk about a point that's here in quadrant 4, I might make a triangle, and inside of there I would make sure it's a right triangle, and then I could talk about this x coordinate and this y distance, whatever this distance is, this distance, that would be my x squared and my y squared. But if I look at this triangle right here, that's also the a squared and the b squared, right? And then the radius would be this total distance between 0 and the edge of the circle. That's my radius, right? X and y. But we also know for this triangle that I just drew that it's also the hypotenuse. And so that would be c squared. So in a lot of ways, this formula right here for the circle comes back to stuff that we've already looked at, that people have been looking at for thousands of years now. A squared plus b squared equals c squared. And you see some nice stuff coming in there. So don't forget that this is very much like the Pythagorean theorem, okay? It's also, it's also very close to the distance formula, which ties in with Pythagorean also. So let me go ahead and say what I was starting to say, which is, what if it's not centered at 0, 0? Then I have to do a bit of compensation, and that particular formula will look more like x minus h squared plus y minus k squared equals r squared, where this h and this k form the x value and the y value of a coordinate point, which is the center of the circle. Okay, so in other words, if it's not centered at 0, 0, if my circle isn't exactly at the origin, centered at the origin, if I shifted it over and then shifted it up, then I would have to compensate for the fact that I shifted it over by figuring out how far left or right did my h go. And I would have to compensate for the fact that I shifted it up or down by figuring out how far up or down did my k go. Okay, so this point here tells me whether or not I'm shifted off of the origin or not. And whenever I look at that, and now if I talk about taking the square root here, then for sure that would look like the distance formula. Let me show you what that would look like. It would be r equals the square root of x minus h squared plus y minus k squared. And if you don't remember the distance formula, let me throw that in here real quickly. D equals the square root of, and it's x minus x1 squared plus y minus y1 squared. That's kind of the traditional distance formula. If you had 2 points that would be unknown, they might have some subscript 2's in there, right? x2 minus x1, y2 minus y1. But that's kind of what the distance formula looks like. And look at how similar those things are. You've got this subtraction between the x values squared. We know it doesn't really matter which one of these comes first, right? Say I had a point, 2 points, and one of the x values was 3 and the other one was 5. 3 minus 5, well, that's negative 2, but when I square it, it becomes a positive 4. Or if I had messed it up and done 5 minus 3, done it in the other order, well, that's a positive 2, and when I square it, it becomes a positive 4. So the order inside of a distance formula, this is not the same as a slope formula or something like that, but inside of a distance formula, your order doesn't matter at all, right, inside of here. And same with your y's. It doesn't matter which one comes first, because after I subtract, I'm squaring, and that's going to make it positive no matter what. It also, by the way, doesn't matter if the x's come first or normally substituting for that second guy. But just kind of a little aside to make sure we know stuff. All right, so questions that might come up that are similar to this are things like write an equation. Centered at -3, 7 with a radius of 2 inches. Or feet or meters or whatever. It doesn't matter. So the equation here is going to be because this is not centered at 0, 0, we're gonna use that second formula, right, where it's offset. But we're gonna have to be a little bit careful. It's x minus because that's in the formula. But then I noticed that here's my h and here's my k, right? I noticed that the h is negative, so I need to throw in a -3. H minus -3 squared plus y minus my k value is 7 squared equals the r is 2 squared. Okay, so there we go with that. All right, negative, negative, that's a positive. X plus 3 squared plus y minus 7 squared is equal to 4. There's my equation. Okay, and I'm not going to do other stuff with that because they want me to leave it in generic form. So the x and the y are just going to stay in there. That's the equation. That would be the answer. All right. Simplify as much as you can, but then once you've got that, move on. Okay, and then similarly, you could work backwards, right? Similarly. So it might say something like, given the equation of a circle, and it looks like this, x minus 5 squared plus y plus, pull that guy down, there he is, okay. The original formula has a minus sign in there, so the h really is the 5, but here the y minus the k, this is a plus sign, so if you need to rework that, y minus -12, but I can see, hey, it wasn't a negative. The negative came in the formula, and then I had to have another negative to make it positive 12 right there, so my k is actually a -12. So h equals 5, k equals -12. So you just gotta kind of sleuth that out and work backwards and say, hey, there's a negative in the formula. And then this guy needs to be my r squared, right? So radius equals 8. Okay. That's not an arrow sign. It should be an ampersand. And let's try that. And radius equals 8. So you just square root whatever number's sitting over there by itself. If it happens to not be a perfect square, then you might have to do a little bit of work with that radical to simplify and stuff like that. But for this one, I've got a pretty nice straightforward example. It's not that bad. Okay, so let's talk about something that maybe we're used to seeing, but not quite in the way that Descartes would have worked with it. So here's a definition for us of a parabola. Okay, a parabola is the set of all points that are equal distance equidistant from a fixed point to a fixed line. We're going to need a little bit more information about that, where the point is called the focus and the line is called the directrix. And one more little note, we're talking about perpendicular distance here. Okay, that one can be a little bit difficult for me to draw sometimes, so I apologize a little bit in advance if my pictures aren't amazing. Okay, so let's talk about this. What we're saying is that we're going to have some point, it's called the focus of the parabola. Okay, so I'm going to cheat, and I'm going to use focus 0, 1, because that's cheating because I'm not moving off of the y-axis any to get my focus. I'm just going to go up. So here's y equals 1, here's the point 0, 1. Okay, so that's my focus. Okay, so I've got that point right there. And what we're saying is we need all the points that are an equidistance from that point. And we'll basically use perpendicular distances. So, okay, well, let's talk a little bit. If I use that right there as my focus, then let's say that the vertex of the parabola is here at 0, 0. The distance here between those guys would be a 1. Does that make sense? Okay, so I'm not moving off the y-axis any. I just have to measure the distance between the y equals 0 here and y equals 1 here. That distance is 1. So I've got this focus here, and I want all the guys who are going to be a distance of 1 from it. So, okay, maybe here on the sides it's pretty easy. Maybe I can see, all right, those are going to hit there at 1 and 1. Okay, because they got to be perpendicularly, -1 and +1, right? They've got to be the same distance. But maybe it's harder to tell exactly how far I need to put things to make this lovely little parabola, okay? And we can... We haven't talked about the directrix at all. So the idea here is that my directrix will be the same distance from the vertex as what the focus is. Well, but underneath it, basically. So the same distance below it. Well, that would be -1, right? So I'll have this lovely line going through here at y equals -1. So that's my directrix. Okay, so, okay, that's not terrible. What I see here is that the gap here is 1 and the gap here is 1. So the total distance between the focus and the directrix is 2. Okay, so whenever I start working things out and I start putting these up here, it's interesting because I'll have these lovely, almost like triangle things coming up here to figure out what's the distance between these guys. For this to be a perpendicular distance, it needs to be on a tangent line, right? It needs to be coming out and meeting the parabola at a tangent line. So if I come up here, for instance, it'll hit this at a tangent line. Oops, that's not a very good 90-degree angle, I'm sorry. But so we'll see that we're having these small little triangles that are developing. And what we're after overall is for the total distance to still be 2. So for instance, it might be that instead of coming up here just 1 unit, I have to come 2 units on to get away from the directrix. But for the focus, it's actually even with it. So on the y values, the distance there is 0. So that's what I'm talking about, that it will be a 0-sum total. So if this distance is 2, then this distance is 0. 2 plus 0 on my vertical distances here is still 2. But if I come way up here and this distance becomes a 3, well, this distance from the focus is now going to be a -1. And now I'll have 3 plus -1 for my vertical distances. And that also will be 3 plus -1 gives me a total distance of 2. That's why I mentioned that as I go up here, as I get higher and higher, that remember these values, the y values, are above what I'm doing here. So as I figure out their distances, I'll actually have negative numbers going in there. All right, so there's some work that happens. Let me just kind of, I'll give you a bit of a flavor for this, but I'm not too worried about you like reproducing this or anything like that. What happens here is that we know that the distance from P to F, where P is any point on my parabola squared, And why are they going to square it? Because we know that this could be a negative. So once I square it, it makes it a positive. And the distance from P to the directrix, I don't know why there's not an abbreviation for directrix, squared, that those two should be equal. Okay, so it's just something that's set up for you. You already know it's there. The interesting thing for us is because the directrix is always, you see how this was, this was y equals -1 when my focus was a positive 1. You see if A equals the y value of the focus, then y equals -A is going to be my directrix. Because it's got to be a horizontal line, so it's going to be y. It's going to be dealing with the y values of the focus, and we're just going to put it an equal distance away on the opposite side. If, for instance, this was an upside down parabola and the focus was below it, so it was a negative number maybe or something like that, then the directrix would be a negative of that negative number, which would make it positive, which would flip it to the other side. So what I'm saying is if you have an upside down parabola with the focus down here, it doesn't matter. Your directrix will be equal distance above it instead of below it. So it all works out in the end. All right, so what we have here, if we're doing the distance between this point, P, y minus, and the directrix, which is a -A square, is that this becomes y plus A squared. Okay, that's not terrible, right? Okay. But, however, the point here, because the directrix is just a y value, but the point here has both an x and a y value, right? So we'll do this. We'll look at the other side. The point has an x value and a y value, so whenever I do that, I kind of need to set it up as the x value of the P minus, in this case, the focus, because we're not moving it off of the y-axis. It gets more complicated when you do that. So the analytic geometry gets a little bit more complicated, but for our purposes, we're not moving it off the y-axis, so that'll be a 0. That guy squared plus the y guy, and it's minus the y value on the focus, but look, in this case, it was a 1. I'm going to make it more general because I'm doing general here. So it was minus A, right? A is the y value on the focus. Okay, so that is my distance of those things. So what we're saying is that these two things should be equal. So, let's talk about that for a second. If I have x minus 0 squared, well, that's just x squared. And if I have y minus a squared, well, that's a binomial squared, right? So that's y squared minus ay, there's going to be 2 of them. They're both going to be negative 2ay's, and then a plus a squared, right? And over here on the other side, so I've got x squared plus y squared minus 2ay plus a squared equals, over here on the other side, this is also just a binomial squared, right? So y squared, again, there's an ay, but these are positive guys, plus 2ay, and again, there's a plus a squared. Okay, so I shouldn't have drawn that quite so long. Sorry, I can't get rid of it. So anyway, I don't need that line that far down. Okay, so what's going on here? On both sides of the equation, I've got a y squared. They're both positive, so I know I can subtract those off. On both sides of my equations, I've got an a squared. They're both positive, so I know I can subtract both of those off. The only thing is I have to be a tiny bit careful here because this is a negative 2ay, but this is a positive 2ay. So you are not able to get rid of those, okay? One's a positive, one's a negative. I can add that 2ay over, for instance, to get the x squared by itself. But whenever I add, they don't go away, right? They just accumulate on this side over here. So it will go away on the left-hand side. So now I've got x squared is equal to 4ay. Okay, so x squared is equal to 4ay. That's what it would normally look like for us if we know that, let me just throw in there, A is the distance between the focus and the vertex, whatever that distance was. We have to have like, hey, what does this A stand for? So that's what we defined it as earlier, so just so that we all know what we're talking about there. All right, so we've got this really cool formula. If you're taking the final exam after a bit, that guy might come in handy somewhere. It's also interesting to notice that sometimes with Descartes, he wasn't just caring about the parabolas that are up and down. So he also has some sections where he works on sideways parabolas. Okay, and you may have seen some of this kind of stuff, hyperbolas, working with different conic sections and stuff like that. But whenever he does that, it basically ends up, he proves in some of his works, it basically ends up that it also works with this same process here, y squared equals 4ax. So if you had a sideways parabola you wanted to work with, you could use a very similar formula, right? We just switch the x and the y, basically. We can just switch them, and then we have a lovely formula that still works, and we go from there. All right, so that's all fun as well. All right, what would we do with this is the question. All right, let me rewrite this guy. So here is the formula for finding the equation of a parabola, Descartes style. Okay, now we know in most algebra classes, we don't normally talk about that, the directrix and the focus and stuff like that. When we're talking about a parabola, let's use the same one we were just looking at a second ago. Okay, we might talk about its vertex. We might plot points. We might have something about whether or not it's in standard form or whether or not it's been reflected or stretched or things like that, shifted and things like that. Those are kind of the way we talk about it in modern algebra, but it doesn't mean that we couldn't still apply Descartes' formula, which, again, I'm just rewriting it so I've got it on this page. All right, it looks like that. Okay, so what kinds of questions might you see on a final exam or something dealing with this? One thing might say something like, right? This one's not bad. Some of them in your book get a little bit worse. Write an equation of the parabola with focus of 0 and 5. So again, that's the point 0, 5, that's the focus. And we have a directrix at y equals -5. Now just for a moment, let me say they don't always have to be centered at the vertex. I happen to know this one is going to be centered at the vertex, and centered at the origin. And the reason I know that is because 1, 2, 3, 4, 5, here is the point that is my focus. The vertical distance here is a 5, right, between 0 and 5. And look, they told me the directrix is at y equals -5. So 1, 2, 3, 4, 5. Here's my directrix. Y equals -5. Again, the total distance there is 5 units. Distance always being positive. It doesn't matter if I'm going up or down, right? So the distance is the same, which means that, oh, okay, I knew my vertex was there at the center, centered at origin 0, 0. Now, it didn't have to be that way, right? If they told me that the focus, for instance, let me give you one. Let's say the focus is still at 5. 0, 5 up here is my focus. But what if I told you that the directrix was at y equals 1? Y equals 1 is my directrix. Well, now you're thinking, oh, so the distance between the focus and the vertex has to be the same as the distance between the vertex and the directrix. Well, okay, there's a total distance in here of what? 4 units total. Okay, I need to split that in half, which means that the vertex for my parabola is going to be halfway, so that, again, this is 2 units and this is 2 units. So it doesn't have to be centered at the origin. This guy would be looking like that, right? However far is between the distance, or between the focus and the directrix, that total distance, for instance here, the total distance was 10 units, right? However far that is, the actual location of the vertex is the halfway point, right? I just happened to be nice and gave us one where, okay, 5 units here and 5 units there puts me at the origin. But like I did here, the total distance between the focus and the directrix was 4, so halfway was 2 units and 2 units. So it does not have to be centered at the origin. We just are. So we know if I have this information here, then we know that the vertex is at the origin. Is everybody good with that? I hope so. All right, vertex is at the origin. Okay, so what do I have from this information? So this was just an aside example. It has nothing to do with what we're doing here. I'm sorry. I'm not trying to confuse you. I was just trying to add extra information, so we'll just kind of do that and not pay attention to it. Okay, so what do I know about this guy? The total distance between F and the vertex is my A value. We already said that total distance is 5, so I know A equals 5 here. I also know that I should be able to use this equation up here for a parabola. So I've got x squared equals 4. Instead of the a, I'm going to plug in a 5. And we know that the y stays generic. So I've got a lovely formula here, x squared equals working with. And we'd be able to see, oh, that thing's being stretched, or oh, that thing's being compressed, or this or that. So we could apply some of our current modern day stuff to be able to see that. All right, so that's one thing that could come back that you would see on a final exam. The other thing that you might see is something more along the lines of find the directrix and the focus. When I have a particular equation given. So when you're given, in this case, I'll make it again kind of a nice equation that we can work with pretty easily. X squared equals 12y. Okay, so again, I need to find the directrix and the focus, and I know that in order to find the directrix and the focus, I've got my focus at 0, and this guy is an A, and I know my directrix is at negative, whatever that guy is, whatever the A is. So basically I'm saying I need to find A here, and I know x squared equals 4ay is the formula that Descartes was using. So I look in here and I say, hey, Dr. Webster was super sweet to me and gave me a number that is indeed divisible by 4. So let's factor out that 4. 4 times something times y. That gives me a 3 in there, right? Okay. So 4 times 3 gives me back the 12. So the A here, this is 4ay, don't forget, from here, the A is a 3. If the A is a 3, now I know some stuff. I know that F is 0, 3. That's pretty good for me. And I know that the directrix is y equals negative 3. I didn't write it down, but that's my directrix. Okay, and so once I find, oh, this guy's divisible by 4 very easily, I can pull it out. What if it wasn't divisible by 4 very easily? Well, then I would still divide by 4, like let's say just for funsies, x squared equals 14y, right? Well, I would still divide by 4, factor it out in the front, and think about it this way. This number here, the 3, was the 12 divided by 4, right? So I can just write the 14 over 4 here. This is really 4 over 1. And whenever I think about it that way, 4 times 14 over 4, this is like multiplying by 4 over 4, right? Which is just a 1. Like if I reduce those out, I'd still have the 4 that I started with, or 14 that I started with, right? So in that case, my A would be 14 over 4 once I factored the 4 out in front and then did this compensation step. So you can still do it. I would still be able to say f is 0, 14 fourths, y is negative 14 fourths. It's just not as pretty, which is why Dr. Webster didn't give us one of those for the notes. So, but they are possible. They are out there, and of course, you guys have the superior math skills to be able to do that, so no worries. All right, so that is all about Descartes, and we're finished with these guys. Next is Newton, and I consider him the last major scientist kind of guy that we're going to talk about. So we will wrap that up in the next set of notes, and I will see y'all later. Thanks. Take care.